The hands are based on the thought process. He has moved the drone up and down, the robotic car, the robotic arms, and so on. So we'll see how many demos we will be able to see it, and we can discuss on it. So basically, you are trying to capture the electroencephalogram, which is nothing but the potential difference picked up from the skull within the electrode. And it is basically a cumulative electrical activity of a neuron from a particular place. So the brain-computer interface is predominantly picking up with the artificial intelligence coming into picture for the last few years. The machine learning, the artificial intelligence is what you have been hearing. We worked on BCI way back 20 years, but artificial intelligence was not fully accepted that time. So whatever we did, it was a discrete work. But now, with AI being in the place, we can generalize it for many applications. So, predominantly, the brain-computer interface will be used in the neurofeedback. It could be treating the brain disease, what is epilepsy, the sleep disorder, the ADHD, that's the learning disability in the kids. It could be to guide you how to meditate. It could be to optimize your cognitive performance. It could be to control your anxiety, typically to decrease your anxiety. So neurofeedback can be used in all of these applications. Then if at all you wanted to take BCI directly into the external world, it could be to control something. For example, if at all you wanted to design the BCI applications for people who have lost their muscle activities, muscle controls, you wanted to enable them to control something. It could be, for the spinal injuries, or it could be people with ALS. It could be, there are different levels of spinal injuries as well, C3, C2, C4 spinal injuries. So, depending on what is left out in their bodies, which we call in the biomedical terminology as a residual activity, I can measure the residual activity in the body, and then based on what is left out in their body, we can use that as a signal to control the hardware. It could be based on your emotions, it could be based on your concentration levels, it could be based on what you are gazing. So we can ask the patient to look at a particular object. So once they start looking at the object, we can able to increase their concentration and control it. Or it could be So it could be based on the stimulus. So I can view a different types of stimuluses. So there are audio stimulus, there is a video, image stimuluses, and induce the emotions in the patient, and then thereby I can control something. So these are all the possibilities in the BCI domain. And Rakesh probably will explain and show you the live demos later, wherein you'll be able to see with a simple thresholding values, you can able to control the hardware without a physical control. So based on just your thought process, you can control some robotic arm or robotic car in the real time. So that is interesting to see shortly. So typically the BCI is required for the high precision application, the stroke rehabilitation where we are trying to collaborate and work. Wherever the bit rate is low, so typically since it is a one-dimensional signal, so the bandwidth requirement will be low. You can do the mood monitoring. So we did one experimentation where we were able to classify your moods. Are you happy? Are you unhappy? Are you excited? Are you sad? So we were able to classify the moods of people. So we had a database of around 60 people, 60, where we were able to train the neural network. We were also able to train the classifiers. And we were able to classify 89 to 93% of the time successfully the mood classifications we were able to do it. So it can be, it can get into the cognitive studies as well. You can check the alertness. You can even check the fatigueness, the drowsiness detection during the car driving and all. So these are all the applications that DCI will definitely involve. This is the data which is very, very scary. This is the data which also throws up the opportunities available in the biomedical signal processing areas. Around the world, there are 50 million patients who are suffering with epilepsy. 90 million people with Alzheimer's. Third one, you see it. It is a stunning statistics. 240 million patients worldwide, they are suffering with depression. And I believe this data, we took it before the corona pandemic, and we firmly believe in the last 6 to 8 months, for different reasons, people across the globe are under depressions. It could be due to their job, it could be due to their salary, it could be due to their social life, it could be due to their uneasiness in moving out, restricted movements, etc. For one or the other reason, this number has increased, and probably we will start work in this area in Bangalore. So we have been trying to put the protocol in place. We would like to focus on this depression and then see how do we help them to come out of this depression for different reasons. Parkinson also is a major problem. So 5 million people. The ADHD, you would have noticed as faculties in a classroom of 60 people, 60 students, each one has got a different learning curve. Especially at the primary school level, we find, different kids have got a different learning curve. So there are many kids who are suffering with this ADHD, wherein their learning curve is totally different than the others. So they respond they could be a slow learner. They may not understand or they may not able to concentrate. It is basically the attention deficit, hyperactivity disorder. So you would have also seen these days the kids are very, very hyperactive. They will not be able to sit in a place for 1-2 minutes. If you recollect as a kid, if our parents used to say, sit here. So we used to sit there for hours without asking them a question. But these days, that 1 hour has come down to less than a minute. So it is something to do with the brain activities. So it could be the attention deficit or it could be hyperactivity disorder. That is what is ADHD stands for. So these are all the issues related to a single organ called as a brain. So it requires to dig into the brain, and as you understand, it is most complicated organ in the body. Though you are listening to me, there may be hundreds of things going into your mind. Though I am talking to you, hundred of things are going inside my mind. So it's a very, very complicated system. So understanding the brain is probably ongoing activities. So these are all the problem statements which are open. And all these problems can be analyzed based on the biological signal called as the EEG. So this slide shows you an opportunity to focus on biomedical signal processing, or in specific EEG signal processing. So I'll not get into that. So in 1875, Richard Carton discovered the electrical properties of exposed cerebral hemispheres of rabbits and monkeys. So he was able to recognize some signals coming out of it. And it was German psychiatrist Hans Berger who evolved this electroencephalogram. So EEGs are require electrodes. So basically it's a transducer to translate your electrical activity, the potential difference. It needs to be picked up, it needs to be measured. So you require electrodes. And there are two types of electrodes. One is the superficial or the scalp electrodes, or it could be invasive electrodes. So non-invasive and invasive, these are the two techniques. We deal only with non-invasive. So whatever we record it from the body. We record it from the surface. We don't go inside the body. So if you go inside, it is an invasive. And whatever I discuss is a non-invasive method. And what we use is a dry electrodes, in the sense you don't need to apply gel, or if at all you wanted to apply gel, it's also fine. It's called as a wet electrodes. And it requires a physical connection to the machine. So you can see the cap and then the position of the electrodes on top of it, and then there's a cable which goes into your computer, or we have a wireless Bluetooth based, Wi-Fi based our own device, which you can find it in our website. It's called the NOBO, the latest EEG data acquisition system. It is just 82 grams, so it goes into your skull. So how do I get the EEG signal? So there is a standard 1020 electrode system. So whatever naming that you see, for example, you see a FP, stands for frontal, okay, frontal lobe. You see T, T3, T5, right? So these are all temporal lobe. C stands for central, that is the CZ, C1, C3, which you can see it here. O stands for occipital, so typically the back side here. So from this is the place where all your the neurons and the connections goes to the rest of the body through this occipital region. So depending on what kind of study that you do, the placement of electrodes depends. However, the position of these electrodes is fixed. It is called the 10-20 electrodes. They are at 10 degrees and 20 degree deviation from each electrode. And this entire brain is divided into two, left and right. So typically all the odd numbers naming is on the left side. So for example, FP1, F7, this is whatever you are seeing is on the left side. So the other side, that is the right hand side, will have even numbers like F2, FP2, F4, C2, like this. So on the left side you have odd numbers, on the right hand side you have even numbers. So this is how it goes. So this is expanded in detail. So this is a top view which you can make out. FP1 is on the left hand side, FP2 is on the right hand side, F7, F8, F3, F4, FZ. This is the CZ. So these are temporal, C3, C4, CZ, C4, C3. These are the central. O1, O2. These are occipital. T5, T6. These are again temporal, and so on. So these are the position of the electrodes called as the 10-20 electrode system. It comes named in the cap itself, so you don't have to worry about the position of it. It all comes with the naming, and the electrodes are fixed there itself. So typically User should be able to control the output. I should be able to modify the signals based on the stimulus, or I can also invoke what is called as the evoked potential. So that is also there through the stimulus. So that stimulus could be audio, video, or image stimulus. So the stimulus can be of different types. So typically in the morning session we spoke about frequency. If you can look at the frequency of your brain signal, the maximum frequency is 36 Hertz. That's it. It is not in kilohertz, it is not in megahertz what your brain produces. It is in simple hertz. So, whenever you are deep sleep or in coma kind of patients that you are seeing, if you measure the frequency of the brain signal, it will be less than 4%. So it's called as a delta. When you are doing a mental activity, the beta will be dominating. So that is between 12 Hertz to 36 Hertz. So you can pick up from parietal as well as the frontal side of your brain. So this is the signal that Rakesh is going to record, the beta, because he is going to do some mental activities. So based on the activity that he does, he will generate this signal, okay? And then based on that, he will control some of the applications. For example, if you are doing a mental imagery, right? So during that, the alpha signal will be dominating. If you are imagining something, the brain signal will be producing between 8 to 12 Hertz, right? So there are different types of signals that we come across in the EEG. So typically, whatever EEG you record, we put a different filters to segregate them into all delta, theta, alpha, beta, mu, lambda, etc. That is one. And then what we do after that is, we go for an averaging of different signals that we record so that the noise is minimized. Or you can do auto adjustment with the known signals, that is the comparison with the standard signals. Or you can apply a Fourier transform to detect different frequencies present in the signal. Whether alpha is present, gamma is present. So I can always apply a Fourier transform and then find it out. So alphas and beta waves were studied since 1920s. So typically when you have closed your eyes, you will be able to see the alpha signal. The moment you open your eye, you'll be able to see a beta signal. So when you are relaxed, okay, so it is the alpha. When you are excited, that means when you are doing a mental activity, that is the beta, which is having the high amplitude. When you are relaxed, when you are sleeping, or when you are going for a deep sleep or a coma kind of a scenario, so it is less than 4 Hertz that your brain will be producing it. So this is a mu signal. I'll just skip because this will not be okay. So P300 is another experimentation that was done long back, since 1965. So every 300 milliseconds after the onset of the target stimulus, there will be a peak that will be generated. So that is what is called as a P300 peak. So it's a evoked potential. So you are invoking, you are inducing by giving some stimulus. So in order to do a letter composition, in order to do character recognition on the screen, so you are concentrating. Okay, so I will ask you to look at P. So you will look at P. Whenever the P comes on the screen, you should concentrate. So whenever you concentrate on a P, for example, so there will be a evoked potential. So it comes once in 300 milliseconds time. So that is what the P300, and it was a accuracy of 95%, or 1 character per 26 seconds. Okay, so that's a P300 experimentation. Rakesh, can we shift the presentation now to the mobile?
Yes, sir.
So somebody has to take Rakesh as a presenter. Yes, sir. Before Rakesh gets to us, I'll just run one video what we did earlier. Yes, sir. Okay, so this is what we did. I'll explain as and when this presentation is going on. So we did two tasks. One is and then the illustration. So it was a stimulus that was given and we recorded the data and you can see here we are able to download it and we will run it now. So one is the letter composition as you can see from the screen here. So we will do the training first. Training will take few seconds and after training we will go into the test mode and then the output will be given to the robo car there, so you will be able to see the movement of the robo car. So use the ANN fuzzy for this. So there are four things. One is letter composing 1, letter composing 2, figure rotation 1, figure rotation 2. Now I am dumping it onto the hardware. So if based on this task, I have asked the robo car to move in the direction, forward direction. Right? So it is still running, so we'll stop it. And then we will change the task. Okay? So I'll do the letter composition. So when I do a letter composing, I want the robo car to come back. So that is a signal that I have given, 1 and 0. So now it will come back. Okay. So in this case, what we had done is we gave a stimulus. We gave a stimulus of letter composition and figure rotation. Okay. And then we took a data of around 40 people with the same task. And then we were able to train the ANN fuzzy and then we were able to generate the output and give it to the robo car. Okay. So I will, I want Rakesh to be enabled to share his desktop. Yes, sir, do it. Yeah, I can also explain that. Never have required.
Can you see my screen?
Yes, yes, yes.
Yes, sir. I download the So yes, today I'll be showing a demo on neurofeedback using a 4-channel EEG device. So right now I'm using a Windows 4-channel device. So as you can see, I'm using the Muse software to collect the EEG data. So what you're seeing right now is the live EEG coming out of the headset. So we take the signal and send it to a signal processor. So you can see it here. So the blue one what you're seeing right now is the raw wave. So the green was the filter wave. So we filter between 3 Hz to 4 Hz to remove all the unwanted components. So then later we need the beta feedback. So we are interested in the beta band. So we filter the beta band from the raw signal. So later we can be able to control the application using the theta wave. So right, I'll show you. So as you can see, and the gold one is the beta wave. So So I set a threshold for this. So suppose the data wave goes above the threshold, so there will be activation of the application. So in the last column, which you can see in the right bar, so that's the thresholding. So whenever the beta goes above the threshold, there will be activation. So I'll show you a demo on this. So the power here moves whenever the threshold is higher than what I've given.